Hello everyone, this is tutorial 4 of our course Linear Algebra. Today we'll discuss linear transformations, its matrix representation and isomorphism. So recall that. Okay, I think I need to. Okay, everything is. So recall that linear transformation means it is a map between vector space V and W which preserve linear structure. What does this mean? T preserved addition and T preserved scalar multiplication. C belongs to the scalar field. Then T is called linear transformation. Linear transformation. There are several nomenclature. If P and W are same vector space, then it is called linear operator. That is, T is called linear operator. And in previous day we have seen an important theorem, rank nullity theorem. So what is rank? Rank means dimension of range space, and nullity of T, this means dimension of null space or kernel, whatever you say. So recall, what is the meaning of kernel? Kernel T consists all vectors V belongs to V such that TV equal to 0, and range space, range T means it is simply T applied on V. That is the whole image. Okay, this is the definition. So we have seen that if dimension of, if we consider this kind of linear transformation, dimension of V is n. Suppose those are n and m respectively dimensions. Then we have seen that dimension of V, which is n, is same as rank of T plus nullity of T. We have also observed that to see a linear transformation is 1, 1, it is enough to check kernel of T is 0. So kernel T consists only 0 vector. Okay. Now from rank nullity theorem, so an important fact, let T is a map from K to P, that is T is a linear operator. Yes, Jose.
Yes, sorry, sir. Then why you written V is equal to W, then T is called a linear operator? Is that a special case of the linearity conditions?
No, this is the definition. Sorry, yes, should have written definition. If P and W are same, then this kind of linear transformation is called linear operator.
Okay, thank you, sir.
Yes, it is just name, but you can also say it is a linear transformation. Special.
Thank you.
Okay. So T is a map from V to V. this is a linear operator. In this case, the interesting thing is that to see T is 1 1 or not, we only need to see this fact, that is kernel T is 0, which is equivalent to saying nullity is 0. But since nullity is 0, then by the rank nullity theorem, by start, rank of T is same as dimension of V. But what is the rank of T? It means dimension of image space. So dimension of range space is same as dimension of V. So in other words, we see that is range space is full V, right? Both have same dimension. So if we take all those vectors, uh, they have same dimension, means uh, those two should be same, right? And this implies this T is on. Okay. So we have used the fact, that is if kernel T equal to 0, if nullity is 0. So if nullity is 0, that is if T is 1 1, then we are getting that T is automatically an onto me, right? So that is an important fact to check something, a linear operator is isomorphic or not, isomorphism or not. It is enough to check kernel of T is 0. So this is remark. T is isomorphism if and only if isomorphism T maps V to V is isomorphism if and only if kernel T equal to 0. Okay. So first of all, what is isomorphism? Isomorphism means T is a linear operator which is both one one and onto. Okay. So this is the definition of isomorphism. So let us state some important fact. In previous day we have also observed an important thing, that is matrix representation. So what does this mean? Matrix representation means, so let us give an example before stating this. Let us consider this linear operator T. Give the name D, which maps R3, which maps P3 over R to P3 over R. So what is P3R? It means polynomial up to degree 3. P3R consists vectors like this. It consists vector A0 plus A1x up to A3x cubed. Okay, 4-dimensional vector space, and all those coefficients AI are coming from real number. Then we want to find the matrix representation of this derivative map. So what is the derivative map? We know derivative of this 1, it is same as 0. Now d of x is same as 1 and d of x square is 2x. D of x cube equal to 3x square. Okay, so we can write it as linear combination of bases. Note that a basis for this vector space P3R is 1x, x squared and x cubed. As you can see that any vector, any polynomial can be written as combination of those 1x, x squared and x cubed. Moreover, those are linearly independent. So this is a basis of P3R. Now what happens is d of 1 is 0. So let us try to write as linear combination of those basis elements. So this is same as 0 plus 0x plus 0x squared and 0x cubed. Again, those the basis is ordered basis, otherwise there will be some issues. And this is similarly 1 0x 0x squared plus 0x cubed. 0 plus 2x plus 0x squared plus 0x cubed. And this is 0 plus 0x plus 0x squared, no, 3x squared plus 0x cubed. Now we can write, so what does this mean by matrix representation? Matrix representation is how the coordinate get mapped. That is, if you give me coordinate of some vector, for example this, here the coordinate is a0, a1, a2, a3 with respect to this basis b. So matrix representation sees how this coordinate map to the coordinate of the image. Okay, so this is the vector v, and after applying t we'll get t v, linear transformation of v, and the coordinate of this tv is given by the matrix multiplication of this representation. Okay, so let us see what is the matrix representation. So matrix representation of d with respect to the basis, say this is b, script b is same as, so first we'll write those coefficient in the first column. Okay, so the coefficients are 0 0 and then 0 0, then coefficient of this in the second column, so 1 0 0 0, and then this in the third column 0 2 0 0, this in the last column, so we get 0 0 3 0. So this will be the matrix representation of this linear operator or linear transformation. Okay, so what we have done is we simply write this in the first column and those coefficient in the second, then this in the third column, and similarly okay. So yes, so if we apply, suppose let v equal to this a0 plus a1 plus a2 a1x plus a2x squared plus a3x cubed. Then TV. So here the coordinate of V with respect to B is a0, a1, a2, a3. So coordinate of TV with respect to B, it is given by here it is dV. It is given by the matrix representation of D with respect to the basis B times V. So it is just multiply this matrix with this a0, a1, a2, a3. So if we multiply, it is simply becomes a0 plus a0 2a1 3a3. Sorry. So this is actually a and this is some v. So it is a times this a0, a1, a2, a3. So it is a1, then 2a2, then 3a3, and 0. And now what uh, which vector is represented by this coordinate? It is simply a1 plus 2a2x plus 3a3 x cubed x square, because those are the basis centers, 1x x square and x cubed plus 0 x cubed, which does not matter. So note that derivative of this thing a0, a1, a2, that is given by this. So the role of this matrix representation is whatever linear transformation is given, you see this linear transformation as a transformation between Rn and Rm. Okay. So you see this P3R, this is identified as R4 because you can take coordinate. For example, this A0, A1, A2, A3, it is same as A0, A1, A2, A3. You can identify it as this vector. So whatever linear transformation is given, you view it as transformation between Rn, Rm. And matrix representation is simply x goes to the matrix multiplication, a times x. Okay, so this is the role of matrix representation. And important property, there are several properties, but I'll state this fact. So if you take the linear transformation T, then matrix representation of T inverse, suppose T is isomorphism, otherwise T inverse does not make sense. T is isomorphism. Then matrix representation of T inverse with respect to B, basis B is same as simply take the representation with respect to B and takes inverse of this matrix. Okay. And I should also mention T is invertible if and only if corresponding matrix representation is invertible matrix. So invertible means isomorphism. Whenever I say invertible, it means isomorphism. Invertible matrix. This is isom. Okay. So those are some important facts. Now let us solve some problems. So in the first question, T is a linear transformation from R3 cross R3 to R3, and matrix representation with respect to the basis, this is given by the matrix A. Now we need to find those T. Okay, so okay, so given let this is E1, this is the vector, not E1, suppose this is alpha 1, alpha 2, alpha 3. So this is the basis. Here all those, there's, you should include transpose. Okay, so what is, so note that 1 1 coordinate of 1 1 1 with respect to the basis B okay 1 1 1 with respect to the basis B is 1 0 0 because this is the first entry in the ordered basis, and similarly coordinate of 1 1 0 with respect to basis B is simply 0 1 0. And what about 1 0 0? It is the third entry, so its coordinate will be 0 0 1. Okay, now we need to see what is the value of, hello, yes.
So, I'm sorry, but I don't understand this part. Wouldn't it not make sense to have a, if you have a 3 by 1 matrix with respect to the basis B, when B is a 3 by 3 basis, would it not make any sense at all? Like, how do you?
Sorry, what is your question?
So you're representing a three. The basis B is 3 by 3 basis, right, sir?
Yes.
So, this what? So how would you? Okay. The basis B is 3 by 3 or 3 by 1.
Okay, so those are 3 by 1 because those 1 1 1 transpose. There is
Okay.
so it is column vector.
Thank you, sir. Sorry.
Yeah. Okay. So, sorry. Now T of this 1 1 1, T of 1 1 1 means it is actually alpha 1. T alpha 1 with respect to B is simply take the matrix representation and simply take alpha 1 coordinate of alpha 1. So the matrix representation is given by this A, right? A is simply this matrix and alpha 1 is 1 0 0. But what is A? A means this 1 1 minus 2 and those, there are several. So let me write. It is 1 1 minus 2, 0 1 0, 0 2 3. So if we multiply, then we will get the first column. And first column is 1 1 minus 2. So that means the coordinate of T alpha 1 with respect to B, with respect to the basis B is 1 1 minus 2. But here it is a different thing. So this is wrong. Now, what about other things, t of 1 0 0. So again, t of 1 0 0, 1 0 0 is same as alpha 3. So t of alpha 3 with respect to b, it is simply multiply this transformation matrix A with the coordinate. Coordinate is 0 0 1. So this will give me the third column. Third column is 0 2 3. So again, this is different. So this is also wrong. Now, sorry, just a minute, just a second. Okay, sorry. So now we need to see t of 0 1 minus 1, right? And
Excuse me.
yes,
We are multiplying with the matrix A. T of alpha 1 with respect to the basis means automatically it is first column of A.
yes, exactly. That is the
Then
thing.
we multiply A and something to get that first column.
Yes, that is clear. But to see the generalized fact how this work, I am. It is clear that 1 1 1 that is same as this 1 1 1. So that will give me the first column, and similarly 1 0 0 is the third thing. So it will give me the third column. So to see the general process, I am writing this explicitly. Okay. Okay. So now t of 0 1 minus 1. So can we write 0 1 minus 1 as linear combination of those three things? So let us see how we can write 0 1 minus 1. So So what will be the value of C1, C2, C3? You see that the last minus 1, this will be occurred because of this first entry. There are no other thing which contains 1 in the third source. Here the last entry is 0, here it is also 0. So C1 must be minus 1, right? So C1 is minus 1. Now if C1 is minus 1, then again, what is the thing? This is minus 1, and the sum should give me 1, right? So we are getting minus 1 plus C2 is same as 1. So C2 must be 2. Similarly, C1 plus C2 plus C3 should be 0. C1 is minus 1, C2 is 2, plus C3 is 0, right? Therefore, C3 is minus 1. Therefore, the coordinate of 0, 1, minus 1 is minus 1, 2, minus 1. Zero, 1, minus 1, coordinate of this vector with respect to B is same as minus 1, 2, minus 1. Therefore, so let me denote it by the vector V. Then TV with respect to basis, it is simply A times this minus 1, 2, minus 1. But as you can see, A is same as this one. 100 112 minus 203. So if you multiply this with minus 1 2 minus 1, what will you get? It is simply minus 1, then minus 1 plus 2 minus 2, again minus 1, then plus 2 0 minus 3 minus 1. So in this case the answer should be minus 1 minus 1 minus 1, but it is 101, so this is again not a correct answer, so C is false. Now what about D? So note that here it is 0 minus 1 1, right? So it is negative of minus, it will be same as minus V. So minus V with respect to B, it is same as negative of this representation, which is 1 1 1. So this is the correct answer. Is it clear how we can find the coordinate of some transformation? Okay. So let us see this question. Here you can see that V is a finite dimensional vector space over a field F, and T is a linear transformation from V to V. Now if rank of T is same as rank of T square, then will it be true that range of T intersection null space of T is 0? So we need to see which of the following are correct. Okay, so let us see the first thing. So it is given that rank T is same as rank of T square. So if range and null space has non-trivial intersection, then assume V belongs to this range T intersection null space of T. Now since V belongs to range T, V can be written as TW for some W belongs to the vector space V. Okay, so let us see what kind of contradiction we are getting because of this thing. So let null space of T, it is as a basis alpha 1 up to alpha k. So that means nullity is k. I am assuming this. Okay. Now what happens? You can see that T alpha is are 0. So that will also imply T square alpha I are 0. Okay. So it means alpha I also belongs to null space of T square. Moreover, T square of this W is same as T of TW. TW is same as V, but V belongs to the null space. V belongs to both range space and null space. So TV becomes 0, right? That means W also belongs to null space of T square. So we are getting those alpha 1 up to alpha k and W, those are, this is a subset of null space of T square, but those are also linearly independent. How we can see? Let the combination Ci alpha I equal to 1 to k plus Ck plus 1 W equal to 0. Okay. If we assume this combination as 0, let us apply T. This will give me T applied on the whole thing equal to 0. Now we use the fact linearity, by which we will get I equal to 1 to k Ci T alpha I plus Ck plus 1 Tw equal to 0. But recall that those alpha i's are element of null space. So T of alpha equal to 0. So we are finally getting Ck, those are 0 plus Ck plus 1 Tw equal to 0. That is Tw equal to 0. But Tw is same as V. So this actually means Ck plus 1 times V equal to 0. Right? V is a non-zero vector. Therefore, we are getting Ck plus 1 equal to 0. Okay. Now, if Ck plus 1 is 0, then sum of Ci alpha I equal to 1 to k is also 0. But those are basis element. Therefore, those are automatically linearly independent. Ci is 0 for I equal to 1 to k. Right? Therefore, this set alpha 1 up to alpha k and W are, this set is linearly independent. Hence, nullity of T square is greater equal to k plus 1. Right? So, uh, nullity. Now we will use rank nullity theorem. So rank of T square, this is same as the dimension of the vector space. Suppose the dimension of the vector space is M, then it is n minus k minus 1. And note that n minus k is rank of T, because we assume that nullity of T is k. Here, nullity of T is k. So this is actually rank of, sorry, this is n minus nullity of T square. This is less equal to n minus k minus 1. But n minus k is same as rank of T. This is rank of T minus 1. From here it is clear that rank of T square is strictly less than rank of T. Right? So we are getting a contradiction. Therefore, this range intersection null space must be empty, must be 0. We have taken a non-zero vector and we are arising at a contradiction. So 1 is true. This statement should be true. And what about the second statement? If rank of t is same as rank of t squared, then V decompose as range plus null space. Will it be true? So let us see what happens in this case. Given t equal to t square. Let this has a basis alpha 1 up to alpha r, and null space has a basis beta 1 up to beta k. Okay. Now those alpha i's are from range space, right? Therefore alpha I belongs to range space. So alpha I is t of some alpha I dash for some alpha I dash belongs to V. Okay, this is true for I equal to 1 to r. So that our claim is that this linear combination will be 0. Okay, so that is, those are linearly independent. That is what is our claim. So let's see sum of ci alpha I equal to 1 to r plus sum of di dj beta j equal to 1 to k equal to 0. Now apply t. So by linearity it will become sum of ci t alpha I equal to 1 to r plus dj t beta j equal to 0. Note that beta j's are element from the kernel, right? So t beta j vanishes. That will be 0. Therefore, we are getting sum of ci t alpha I equal to 0. But here, from here, we see that alpha is same as t alpha I dash. Therefore, t of alpha I is same as t compose t, which is t square of alpha I dash. But it is already given t is same as t square. So this is okay. So we get t square is same as t alpha I dash, and this is simply alpha I. Okay, it is already belongs to the image, so if we again apply t, we will get the same thing. So we are getting ci alpha I, this combination is 0. But those alpha i's forms a basis, therefore those are automatically linearly independent. This will imply ci equal to 0 for I equal to 1 up to r. Now ci are 0, therefore the second part, this sum of dj beta j equal to 1 to k is also 0. We note that those beta j's are also linearly independent because those are element coming from this basis. Okay, so dj's are also 0, j equal to 1 to k, right? Hence what we are getting is alpha 1 up to alpha r, beta 1 up to beta k. this set is linearly independent. Okay, so something is linearly independent, but we know that by rank nullity theorem, dimension of the vector space V should be same as rank plus nullity. Here rank is R and nullity is K. So we are getting that this should be the basis. It is forcefully because those R plus K is same as dimension. Okay. Therefore, V is same as V is generated by those vectors, and alpha 1 up to alpha R spans image or range, and beta 1 up to beta K span null space, NT and RT. So this is how we can see that second option is also true. Up to this, is there any doubt? Okay. If not, let us see the third option. Now, there is no condition. We need to see if there always exists some positive integer k for which v is same as range of t to the power k direct sum null space of t to the power k. So, in previous question, there is a condition for which v can be decomposed as range plus null space. But here we don't have any condition. We need to see if there exists any positive for which this is true. Okay. So in this, in the third part, we need to observe a fact. So the fact is, range of t is a subspace of V, and again, range of t square is a subspace of range of t, and it will continue like this, right? In the dual part, we also see this kind of thing, that is null space of t containing null space of t square. So it will be opposite kind of inequality. All are subspace of V. So this is not needed, but a fact. So range are actually shrinking. Range of t to the power n will be subspace of range of t to the power t square, and so on. So from here it is clear that all there should be a bound which is 0. So there exists some k such that range of t is same as range of t square. If that is range of t to the power k is same as range of t to the power k plus 1, there must be such k, because all those things cannot be strict. V dimension of V is finite, so the length of the chain can be n. There cannot be more strict inequalities. right? So it must stabilize. Okay. So if this is the case, then now we can use this previous observation. Okay. And then if we use this observation, then we can prove that V is same as range of T to the power k direction null space of T to the power k. Instead of T, we are actually using T to the power k and T to the power k plus 1 here. Okay. So from here we are getting rank of T to the power k is same as rank of T to the power k plus 1. Hence, we will get the result that V can be written as range of T to the power k plus null space of T to the power k. Okay. So this option is also correct. One, two. So this is the correct thing. 1, 2 is true, are true, and the statement 3 is also true. Okay. This is another question. Here we are considering V a finite dimensional vector space and T is a linear transformation from V to B, that is a linear operator. Then T is 1 1 imply T is on. Is it correct? Can anyone answer this?
Yes, it's correct.
Yes. So why will it be true?
Because the range of T is equal to the whole domain. So if it's 1 1, then it'll cover the whole range already. The domain and the codomain will be equal.
Yes. So the idea
Actually,
is,
sir, it is finite dimensional. So actually, the logic is true, but mainly occurs for finite dimensional.
yes. So for finite dimensional, which theorem will you want to use in this case? You use this rank nullity theorem, right?
Yes.
So here it is 1 1, therefore nullity is 0. Okay. So rank plus 0, rank plus nullity is same as dimension of the vector space. So that means rank of the transformation is same as dimension V. In other words, range of the transformation is V. So T is becoming 1 1, 1 2. Okay, 1 1 implies 1 2. Now what about the second one? If T is 1 2, then T is 1 1. Will it be true?
Yes, sir. You just have to reverse the logic because
Exactly. Exactly. We just need to reverse. That is, if we write reverse direction, then we'll get the same thing. Okay. So 2 is also true. Now T is isomorphism if and only if T is 1 1. So this is also true because of, we already know that if T is 1 1, then T is automatically on 2, and 1 1 plus on 2 will give me the isomorphism. So this is also true. The above properties hold even if V is infinite dimensional. Will it be true? So will the above property hold for infinite dimensional vector space also? Okay. So there will be some issue. Let me give an counter example. So consider this map T from R infinity to R infinity. So think it as n-dimensional vector space, but n is now n tends to infinity, so it is becoming infinite dimensional vector space, and the operator sent t of x1 x2, this is same as 0 x1 x2, this. So it is a shift operator. Now can you see that t is 1 1 or not? Can you see if it is 1 1? So it is clearly 1 1. Why? Because if t of this thing, t of x1 x2 xn x, this is 0, then clearly 0 comma x1 comma x2, all those component will be 0. So xi equal to 0 for all I. Therefore t is injective. But can you see that though t is injective, but it is not 1 1, it is not 1 2. Can you see that?
Yes, sir.
Yes. So which element does not belongs to the range?
X x1 to xn without any initial 0.
Yes. 1 0 0, this kind of element everywhere 0, it does not belongs to range.
So the
Okay. Yes. What is your comment?
no, sorry, I was just saying. So none of the properties hold.
Yes. So t is not on 2. Okay. Can you construct another direction that is injective but not on 2? Can you construct another example where it is on 2 but not injective? So 4 is false. Can you construct an example where it is on 2 but not injective? So the process will be similar. Instead of shift in the right direction, we shift in the left. So take this example: x1 x2 x3 dot dot is same as x2 x3 x4 dot. So in this case you can see that image will cover everything. All elements belongs to the image, but the kernel is non-empty. Kernel is non-zero, sorry. So can you give an example? Can you see what will be the kernel of this transformation? Kernel
Just
of this,
translation actually.
yes,
Anything where x2 to xn is 0, but x1 can be not 0 or 0. That doesn't matter.
exactly. In this case, kernel of t will be x1 0 0. Everything is 0, but x1 can be anything. X1 belongs to real number. So it is not injective, but it is onto. Okay. So before that, let us see another example. We have already seen that T is isomorphism, means it is 1 1, and it is also onto, injective and surjective, and this is equivalent to saying matrix representation of T is invertible. Okay. So let us try to see if something two vector space are isomorphic or not. V and W are said to be isomorphic if there exists a linear transformation T map V to W which is isomorphic. So instead of linear transformation, we can directly say linear isomorphism. Okay, from V to W. So let me put a question. Which of the following are isomorphic vector space? R2n over R, Cn over C, Cn over R, and Cn over C. And polynomial up to degree n over R. So it is PNR means it is already over R, but I am writing again. So can you see which of the following are isomorphic vector spaces?
So the first one is not. The it if the size is equal, then only they can be isomorphic vector spaces.
Yes, you are right. But what do you mean by size of a vector space?
If every element of the vector space can be put in a one-to-one correspondence.
Yes, that is okay. But can you simplify it
Oh,
in terms of
sorry, the
dimension?
dimension.
Okay. So if two vector spaces have same dimension, then those two vector spaces are isomorphic. Okay. So here, can you see what will be the dimension of R2n over R?
2n, sir.
2n. So what will be a basis element of this? It is simply E1, E2 up to E2n, where EI means 1 at ith component and every other components are 0. Now what about Cn over R? So in this case dimension is n. Here dimension is 2n. Sorry. Now what about Cn over C? What will be the dimension in this case?
N, sir.
N. So how can you see the dimension is n? What will be a basis element for this?
Basis element is the set of complex numbers.
Yes, that is correct. But can you give me a basis, ordered basis for this Cn? For example, for C, what will be the basis for C? Or what will be a basis for R, real number over real number? The basis is 1. If we take R2, the basis will contains 1 0 and 0 1. So that is similarly what will be the basis of Cn over C? Can you give me an ordered basis? So the same thing, you can choose the same entries, same E1 up to En, right? E2n, En, sorry. Here E1 means it is 1 and every other terms are 0. Similarly, E2 means 0, 1 and every other terms are 0. So take a complex number, whatever complex number is given. For example, 1 plus I and 0, 3 plus 2I, like this. There are some, suppose all other terms are 0. Then what will be, can you represent it in terms of basis? It is simply, yes, tell, what will be the answer?
It would be simply E1 plus E1 into I plus E3 into 3 plus E3 into 2I.
Yes,
Oh,
but
E1 into 1 plus I plus E3 into 3 plus 2I.
exactly, because the field is complex number,
Yeah,
so
it's
the
overcome.
coefficient is okay. You can choose complex number. So 1 plus I E1 plus 3 plus 2I E3. Okay. Now, so in this case, the dimension is n. Now, what about Cn over R? Can you give me a basis? Can you give me an ordered basis for this? Cn over R. Go ahead. So, again, just simplify this problem. What will be a basis for C over real number? Any element of C will look like A plus Bi, right? So, can you write it as combination of some vectors which will be linearly independent?
1 comma I.
Exactly. So this can be written as A times 1 plus B times I. So here C over I R has basis 1 comma I. Let me put in uh, second bracket, otherwise this may make some confusions. This, so I am writing first bracket because those are ordered basis, but okay, second bracket is also. So 1 comma I is a basis for complex number over real number, over the field real. Now what about Cn over R? So can you give me a basis? The similar, same.
Yeah, 1 comma I n times.
No, it is E1, E2, En, comma I.
Yes, both of you are correct. So 1 comma I, but you need to put in component wise. For example, instead of E1, we also need to take this I 0 0 up to 0, right? But note that this is same as I times E1. Okay. So those those are E1 up to En, and let me write the notation E1 dash for this kind of I comma 0 0. Similarly, EI dash will represent I at ith entry. Okay, so E1 up to En, and then E1 dash, E2 dash up to En dash, where EJ dash means it is defined by 0 I at jth place and 0 else jth place. Now, what about, so in this case you can see the basis contains 2n many element, 2n many vectors. Therefore, dimension of Cn over R will be 2n. Dimension is 2n. Now, what about polynomial PNR over R?
N plus 1.
N plus 1. Exactly. So, can you give me a basis? is simply 1x x square up to x to the power n. So dimension is n plus 1. So in this case, only those two things are isomorphic, R2n over R and complex number over R, Cn over R. So 1 and 2 are isomorphic, 3 is in different class, 4 is also in a different class. These two are also not isomorphic. Okay. So this is a notation. The isomorphism V to W is written as this. Instead of equal, we put this kind of symbol, congruent, V con W. And if two spaces are not isomorphic, simply cut this congruent sign. Okay. Now let me give some other examples which you can answer now. Which of the following are isomorphic? The subspace of symmetric matrices. The subspace of skew symmetric matrices. So here the main vector space V is MNR, that is set of all matrices whose components are real number. The subspace of matrices with trace equal to 0. Now what is your answer? Which of the following will be isomorphic? Okay. Okay.
I said this subspace of symmetric and skew symmetric are isomorphic. Those two are isomorphic. Then subspace of matrix is. I'm not. I just checked.
Oh, sorry. I think there are some issues. Ah, sorry. I need to reshare. Yes. What are you saying?
So the subspace of symmetric matrices and the subspace of symmetric matrices are isomorphic.
Okay. Why those two are isomorphic?
So those two are isomorphic because both allow for the same degrees of freedom. Meaning, when you're creating a symmetric matrix, you can choose all of the this in the upper triangle.
Okay.
Uh,
So, what you are suggesting is is in the right direction, but there is some few issue. So let me reduce the problem. Instead of
First one,
n by n matrices,
the first one is of rank n into n plus 1 by 2. The
yes,
second one is of rank n into n minus 1 by 2.
yes, what he is suggesting is correct. That is, you can see that dimension of symmetric matrices and the dimension of skew symmetric matrices are not same. Okay, why those two are not same? Let us try with. Let us simplify this problem. Consider M2 by 2 matrix. So what is the definition of symmetric? It means A transpose is same as A, right? So
matrices, diagonal elements are not necessarily zero. So it is n into n plus 1 by 2.
yes, this is okay. Let us see what happens for 2 by 2 case. Okay. So symmetrics mean A11, A2 1 2, A2 1, and A2 2. So you can flip it around this along this diagonal. So A12 should be same as A21, right? So in general, what is happening is that A11, A12 up to A1n and A22 up to ANN, you can choose independently all those entries, right? But the entries below the diagonal are determined by all other entries. For example, A21, it is same as A12 because A transpose should be same as A. So all those entries below the diagonal are automatically determined by the entries above the diagonal. So you only need to count the entries above the diagonal and entries in this diagonal. So can you count this? So here there is only one element, then a n minus 1, then there will be two element up to n element. So the sum of in the first row there are n element. So sum 1 plus 2 up to n is same as n times n plus 1 by 2. So those are determined by entries above the diagonal. Okay. So from here the observation is that dimension of these symmetric matrices. So let me put this vector space as W1. So dimension of W1 is n times n plus 1 by 2. And the basis will look like this. So if we consider 3 by 3, then basis will be, let me not give the basis, it will be difficult to write. But 2 by 2 I can write. It will look like 1 0 0 0. So diagonal you can choose independently, there is no issue. But if you choose this entry, then this is automatically determined. So this will be a basis for 2 by 2. Note that it is 2 times 2 plus 1 by 2, that is 3. Dimension of symmetric matrices will be 3 for if we consider n equal to 2. So here dimension is n times n plus 1 by 2. Now what about the subspace of skew symmetric matrices? What will be the dimension? Can you answer there? So
n into n minus 1 by 2.
exactly. So here the restriction is that the diagonal entries, what will be the diagonal entries in this case? So by this condition AII is same as AII transpose is same as minus AII. But sorry, not transpose, but that is Aij is same as minus AII minus AJI. So using this we are getting AII is 0. That is diagonal entries vanishes in this case. And note that whatever you choose, for example, if you choose A12 here, then this element is automatically minus A21 because of skew symmetricness. Similarly, A13 will give me minus A, sorry, 12 minus A13 here, like this. So whatever matrix is there, you can always write it as combination of this many thing. Whatever number is there, you can write it combination of those elements. For example, this can be written as 0 plus A12 times everything is 0, and there is 1 and minus 1 here. Okay, plus A13 times everything is 0, 0, 1, 0, 0, minus 1, like this. So it will continue, and you can see now the choice is n plus n into n plus 1 by 2, but diagonal is not there, so you need to subtract this n. Okay, therefore dimension of the skew symmetric matrices, the space of skew symmetric matrices, is simply n into n plus 1 by 2 minus n, which is same as n into n minus 1 by 2. Now what about the last one? Skew the matrices with trace 0. Can you find
N square minus 1.
exactly? So in this case, you see that the matrices will look like Aij, that is everything is there, but the diagonal entries should add up to 0. That is A11 plus A22. This is Aij up to ANN equal to 0. So from here you can say ANN is completely determined by other diagonal entries minus A n minus 1 n minus 1. So okay, so this is the, so basis will be almost same as Eij. Basis will look like Eij, where I not equal to j. So Eij means those elementary matrices, one at ijth entry and everything else are 0, and you need to take union of. So if you take, for example, if the diagonal contains 1 here, then automatically this element will be minus 1, right? So other element will look like E11 minus ENN up to E22 minus ENN En minus 1 n minus 1 minus En. So dimension is n square minus 1. Therefore, all those vector spaces are different, right? W1 and W2, those two are not isomorphic, their dimension are not same. Those two are also not isomorphic, and similarly those are also not isomorphic. Okay. So instead of doing this question, let me solve this limited time. Okay. So we need to find the dual basis of this basis of C3 complex, three-dimensional complex number, complex plane. So what is the meaning of dual space? Let V be a vector space. Then the transformation of this form, linear transformation from V to F, F is the field. Then this kind of transformation, linear transformation, where codomain is field, is called linear functional. Okay. So V star, the dual of a vector space, it means the space, the vector space of all linear functional. Okay. So the vector space of all linear functional F from V to C, V to R. In this case, it is C because V is a vector space. So we need to find a basis for this V star. Okay. An important observation is that this V star is generated by the dual basis. So what is dual basis? Suppose alpha 1 up to alpha n is a basis for V. Then the dual basis, corresponding dual basis, in the notation it is written as alpha 1 star up to alpha n star. So alpha 1 star will send the vector alpha 1. So those are linear functional. Note, it is the vector space of all linear functional. So those notation alpha 1 star up to alpha n star, those are actually linear functional. So alpha 1 star is a map from V to F, the field F, which sent alpha 1 to 0, alpha 1 to 1, and every other basis entries to 0. Alpha 1 star alpha I equal to 0. Yeah, thank you. So when I is not equal to 1. And similarly, alpha j star, it is defined as alpha j star applied on alpha I equal to 1 if j and I are same, otherwise 0. If j is not equal to 1. Okay. So in this question, we need to find those dual bases, those linear functional alpha 1 star up to alpha n star. Okay. So let us see what will be the dual basis. So basis for C3, it is already given. Usually we take those kind of simplest kind of basis where the first component is 1 and other are 0, and similarly all other entries. But here the basis is slightly complicated. So let me denote those entries as alpha 1, alpha 2, alpha 3. Here, so this is the base theoretical part. Okay. In this question, alpha 1 is 101. Instead of here, let alpha 1 is 101, 1 minus 10, and 20 minus 1. This is alpha 2, this is alpha 3. So we need to find the functional alpha I star. Okay. So yes. Let alpha 1 star is same as alpha 1 star at applied at ABC. Alpha 1 star means it is a function from C3 to the field C. Okay. So let alpha 1 star applied at ABC is same as A x1 plus B x2 plus C x3. Okay. Then by definition of dual basis, this alpha 1 star, it will, if we apply alpha 1 star at 101, that give me 1, right? Alpha 1 star applied at alpha 1 will be 1 and rest of the terms will be 0. For example, alpha 1 star applied on alpha 2, which is 1 minus 1 0 is 0. Alpha 1 star at alpha 3, 2 0 minus 1 is also 0. So the first one will be same as x1, just put the value of a, b, c. It is x1 plus 0x2 plus x3 equal to 1, and similarly x1 minus x2 plus 0x3 equal to 0, x1 2x1 plus 0x2 minus x3 equal to 0. Similarly, if we consider alpha 1 star, so we need to solve this problem. That is, we need to find x1, x2, x3 for which we get 1 0 0. Similarly, if we similarly for alpha 2 star, similarly for alpha 2 star, the equation will look like, so let me denote it by ax. This is a times x equal to 1 0 0. Similarly for alpha 2 star, instead of 1 0 0, only this equation will give me 1 here and rest of the thing are 0, right? So we get a times x equal to 0 0 0 0 1 0, and for alpha 3 star we get another equation ax equal to 0 0 1. So we can put all those equations together. Okay, so we need to find instead of small x, now we need to find a 3 by 3 vector which is same as those things 1 0 0 0 1 0 0 0 1. So it is nothing but to find inverse of A, right? So again we just use row reduction kind of technique. So here, as you can see, A is the coefficient matrix 1 0 1 1 minus 1 0 2 0 minus 1, and the x will be first entry 1 0 0, then 0 1 0, that is the identity matrix 0 0 1, and you need to find the inverse using row operation. So again we perform the operations, row operations. So R2 minus R1, and then R3 minus 2R1. So first row is fixed 1 0 1 1 0 0, then 0 minus 1 and minus 1 minus 1 1 0, then 2 minus 2 which give me 0 0, and then minus 1 and minus 2 which is minus 3, there will be minus 2 0 and 1. Now what we can do is 1/3 of R3 minus 1/3. So everything remain fixed. Let me copy this whole thing. Everything will remain fixed, only the third row minus 1/3 we multiply with minus 1/3, so it is 1 plus 2/3 0 minus 1/3, and we similarly we can also multiply negative sign with the second row, so it becomes plus 1 plus 1 plus 1 minus 1 0, and then R1 minus R3 and R2 minus R3, so that the last term get cancelled. Those terms we need to cancel those terms, so we are subtracting R1 minus R3 and R2 minus R3. Okay, then it will becomes 1 0 0 0 1 0 0 0 1. This side is easy to calculate, we already know, but here we need to calculate. So 1 minus 2/3 which is 1/3, then 0, and then 0 plus 1/3 which is 1/3, and 1 minus again 2/3 1/3 minus 1 and plus 1/3. So the last row remain fixed. So this should be the answer. So those will be the solutions, right? This will give me the solution of the first equation. Sorry, Ax equal to 1 0 0. The second column give me the solution of the second equation, and similarly the third. Okay, so therefore alpha 1 star. So for alpha 1 star, the solution is, for alpha 1 star solution x small x is this 1/3 1/3 2/3, right? Therefore we need to write alpha 1 star as this combination, which is ax1 plus bx2 plus cx3. Therefore alpha 1 star abc is 1/3 x1 plus 1/3 x2 plus 2/3 x3. Similarly, so if we use the second column, this column, then we get alpha 2 star ABC is minus x2, because 0x1 minus x2 plus 0x3, which is minus x3, and alpha 3 star ABC is x1 by 3 x plus x2 by 3 minus x3. So x1 by 3, or we can write minus x2 plus x2 by 3 minus, like this. So let me compare with the question. Here you can see the, sorry, I am extremely sorry, those are ABC, because we are putting the value of x1, x2, x3. So first one will be a plus b plus 2c by 3. So this is okay. Then minus b, and then a plus b minus c by 3. So A is the correct answer. Is the process understood?
Yes, sir.
Okay, great. So this is how you can solve this dual basis. You can find dual basis with respect to any non-standard basis. Okay. So whatever I have said, let me repeat why. So linear transformations from V to W, if we fix those vector spaces V to W, V and W, then if we take all the transformation, linear transformation forms a vector space. Okay, so this space of all such linear transformation, this is denoted by LVW, right? And similarly, if we fix, if V equal to W, it is simply, in short, it is written as LV. Here both domain and codomain are same. Okay. So the interesting fact is that those are also a vector space. Why? Because if you represent VW as, that is, if you take the coordinates V, then the transformation from VW, those are nothing but matrices. So T with respect to some basis, if you fix basis B and beta B dash, this will be simply a matrix. And you already know that set of matrices form a vector space. So this is the idea why this forms a vector space. You can also directly calculate that sum of any two operation, two linear transformation, this is also linear. Okay, so that is an important thing. And moreover, if T is a transformation whose matrix representation is A, M, and suppose S is another transformation whose matrix representation is N, then this composition T compose S has matrix representation N times M. So this is also an important. Here S is a map from V to W, and T is a map from W to U, another thing. Okay. Then the composition, the matrix representation of composition is given by n times n. This is also an important fact. You can use this fact to solve several other problems. So I am stopping at this. If you have any doubts or any question, you can ask. Is there any question? Since
Hello.
there is no question.
Good evening.
Yeah.
Shall I ask a question on already published assignment?
Yes.
The assignment day before yesterday released, sir. Even I
Yes.
raised the query on the question answer forum as a discussion forum. Till now it is not answered. Actually, what happens, sir? Question week 3 assignment 9 was given. One second. Let me take, sir. One second. I think some answer was there, sir. Sorry. Some answer was given.
Okay. It's okay.
When I asked what they given, once again. So actually what happened, question number 9, if you take, sir. Question number 9, maximum rank can be 2 by 2 matrix can be 2. But what they given answer, one of the answer is that rank can be 4 like that they given. But 2 by 2 matrix, how rank can be 4, sir?
Yes, that is then wrong. But can you tell me the question, that is tell the
Assignment week 3, sir. Question number 9, sir.
Can you state the question? What is that?
Yeah. For each matrix A in M2 of R, means matrix 2 by 2 of R, they define a map EA from M2R to M2R. Matrix I, transport of A of B equal to AB. A of B equal to AB.
Yes.
So there are 4 options given. Out of that, only 2 is correct, which I marked. First one is TA is a linear map, which is correct and accepted answer also.
Yeah.
Second one is, third one is the cardinality of the set. That also I am not chosen, but they also the wrong answer they didn't take, so answer was right. Final fourth, myself and both are same. But second question, TA is second option. Second option, TA is injective if rank of A equal to 4. This is the option given. Since M2 of R, how rank of A equal to 4 is possible, so it is ruled out. I thought I didn't selected, but in the answer list, that also a right answer like that they given, sir.
Okay, so
if rank of A equal to 4.
In this case, you can say the problem is wrong. So rank
I given a query also for asking additional mark. Because of that, I lose mark also.
Yes, so you may ask them to re-evaluate.
Okay, you are not directly linked with them, sir.
Yes, I cannot handle.
Okay, sorry, that's what I asked.
But you are correct. That question does not make any sense. So
Yeah.
instead of
Excuse me.
Yeah.
By rank of T, they mean only dimension of the range space. So it is not the rank of the matrix. Rank of the transformation T is rank T is dimension of the range. That
Okay.
range space is 4.
So, but
That
then
is
in that case, sorry to interrupt. In that case, question should be different, na, sir. Question clearly mentioned about rank, na. It's not
rank
in.
of, rank of the transformation, not rank of the matrix.
Oh, sorry.
Okay, if rank of the transformation, that means rank of the rank T, that is dimension of the image. In that case, it is okay. You can-
Okay, sir. Thank you. Thank you for the clarification. Thank
Yeah,
you, sir.
you are welcome. Thank you for attending. So let us stop here. Thank you for joining. Thank you.
Thank you, sir. Thank you. Thank you all.
Kulan, do you want to ask anything? Okay. So let's stop.